Alright, so again, I'm at a hotel, I'm near an airport, there's going to be noise, it's going to be fine. So this is a really cool exercise because anytime you can say anything about an arbitrary function, you are saying a lot. Now this isn't entirely an arbitrary function, this is an arbitrary function from RD to R. So going from RD to R already puts a lot of you already have a lot to work with because you're working with nice metric spaces. But this result is really surprising. I don't know if it's surprising, but it's really interesting that you're able to say a statement like this. The set of points at which f is discontinuous is measurable. Because if it's measurable sets are really difficult to understand, and there certainly exist sets which are not measurable. And if you look in the first few pages of Fallen, you'll find a really good example. You just take the rationals and you shift them by every real number, and then you take one element from each set and put them all together, and you end up with the set which is not measurable. So there's at least one entire class of non-measurable sets, and they're presumably all over the place. But you can even if you have a set like this, which is not measurable, or the set of discontinuities, you can imagine maybe there's a way to construct a really weird function, which has a whole weird set of discontinuities, and the set of discontinuities is so weird that the set of discontinuities is a non-measurable set. But turns out this is not the case. Alright, so let's prove this. So we have these functions, I'll call them f upper delta and f lower delta. And we need to prove that they are semi-continuous. So let f delta of x just be the way that's defined here, the supremum over all x over all y, such that this distance is less than delta. So the way that I'm going to write this is the way that I sort of think about this. This is the image of, or the supremum over the image of the ball of radius delta centered at x. So you take every point in the ball of radius delta centered at x, again this is an RD, you take all these points and you see where they map to under the function f, and then you take the supremum over all of these numbers. Okay, so to prove f delta is what's here? We want this to be lower semi-continuous. It suffices by exercise 1.3.5 to prove that the set of all x such that f upper delta of x is less than or equal to a is closed for all a. Remember, in that exercise we proved that these are equivalent conditions. Okay, so let a be an R, and let xn be a sequence in the set of all y such that f delta of y is less than or equal to a. And suppose xn converges to some x in Rd. So what we want to prove is that f delta of x, which is precisely the supremum over all points in the image of the ball of radius delta centered at x, is less than or equal to a. So let y be any point in this ball of radius delta at x. So what we want to use here is we want to use the fact, So these xn's are converging to x, and if you choose any point in the ball of radius xn, if you choose any point in the ball of radius delta centered at xn, and you map it under f, we know something about this number. And we want to use that to our advantage. So if we let y be in this ball of radius delta x, then, and this argument, this is something that you might work backwards to find. Then x minus y, the distance between x and y, is strictly less than delta. And since xn converges to x, there exists an n large enough such that the distance between xn and x, remember, as n increases, this distance needs to converge to 0, so we can choose an n large enough such that this distance is as small as we need it to be. And it turns out we need this distance to be less than delta minus the distance between x and y. This is going to be a positive number since x and y are, since this distance, so this is obviously going to be, this cannot be exactly delta. This will be some number between delta and 0 because the distance between x and y is some strictly positive number which is greater than delta. Well, wait a minute. What if x is... what if y is x? That should be fine. So I guess it could be delta, but don't worry about it. So then, the distance between xn and y is equal to xn minus x plus. So this is a standard technique in analysis. We're going to use the triangle inequality. Instead of, to get something about the distance between x and y, we're going to use an intermediate point x. Okay, so by the triangle inequality, this absolute value is less than or equal to this. But we know something about the distance between xn and x. This is strictly less than x minus distance between x minus y by our choice of n. And then we have this. Oh, but these two cancel out, and so this is precisely delta. And so y is in the ball of radius delta centered at xn. And now, so that's really what we needed. If we choose any point in the ball of radius delta centered at x, what we really need is we need to find some ball of radius delta centered at xn which contains this y. And this should make sense that such a thing exists, because if you look at the ball of radius delta centered at xn, these balls will get closer and closer and closer to overlap to being precisely the ball of radius delta centered at x. So it makes sense that you should choose an n, be able to choose an n large enough so that this ball will contain y. Okay, so there is some n such that y is in the ball of radius delta centered at xn. Now we know the supremum over all points in the image of the ball of radius delta centered at xn is less than or equal to a. And why is that? This is because xn is a sequence in the set of points such that f delta of y is less, or this is a, xn is an element in the set of all points z such that f upper delta of z is less than or equal to a. So in particular, f upper delta of xn is less than or equal to a, which means precisely that the supremum is less than or equal to a. And if this supremum is true, so in particular, if you choose any point in the set over which you're taking the supremum, you can't surpass the upper bound, or you can't surpass the number that you get from the supremum, because otherwise it wouldn't be the supremum. So in particular, f of y is less than or equal to a. So y this holds for all y in b delta x And so, if you take the supremum over f of b delta x, then this supremum is going to be, so every single point in f of b delta x is less than or equal to a. So if you take the supremum over this set, the supremum must also be less than or equal to a. Because if it were greater than a, then there would be some point in b delta x such that f of this point is greater than a, which we proved is not possible. So this holds, so this, and so the supremum is less than or equal to a. And thus, this means precisely that x is in the set of points such that f upper delta of x is less than or equal to a. And this holds for all x, or this holds for any convergent. So any convergent sequence in f delta less than or equal to a contains its limit point. So thus f delta less than or equal to a is closed for all a and r, and so f is lower semi-continuous. And that's what we wanted to prove. Alright, and then we also need to prove that f lower delta of x, which is precisely using the same notation, the infimum of the image of the ball of radius delta centered at x, is upper semi-continuous. Here we're not going to, we could reprove everything the way that we did previously, but instead we're going to take a shortcut. Note that this is a useful fact about supremums and infimums. So minus f delta of x, this is minus the infimum of this thing, just using the notation that I just did. And you can actually bring a minus sign inside an infimum and it becomes a supremum. So this is supremum over minus f, ball of radius delta centered at x. So this is negative f upper delta of x. So this upper delta thing is it's some sort of operator which you plug in a function and it gives you a function. So for f upper delta, you start with your function f and then it gives you a new function f upper delta. Here we're doing the same thing, but instead of plugging in the given function f, we're plugging in negative f. Now we know g delta so what do we know about this? We know that if you take f upper delta of x, f upper delta is a lower semi-continuous function for any f, and minus f is a function. So we know minus f upper delta wait a minute. Okay, so let me write this out. And so minus f delta, minus f of this thing, so minus f this is lower semi-continuous. Right, okay, because if you take any function and if you apply the upper delta operator to any function, you get a lower semi-continuous function. So in particular, applying the upper delta operator to negative f gives you a lower semi-continuous function. And so minus f of delta can be written as the upper delta operator applied to some function, which means that it's lower semi-continuous. And if you have the negative of if you take a function which is lower semi-continuous, its negative is upper semi-continuous. And so negative f of delta, negative of f lower delta, which is just f lower delta, is upper semi-continuous. And that's what we wanted. All right. So we have that f upper delta is lower semi-continuous and f lower delta is upper semi-continuous. So now we want to prove that the set of points where f is discontinuous is measurable. All right. So there's a little bit of work that we have to do to get there. So we're going to let f0 be the limit as delta decreases to 0 of f upper delta, and f sub 0 is the limit as delta decreases to 0 of f lower delta. Since f upper delta and f lower delta are real valued functions, and they are Borel measurable by theorem 1.5. Wait, since these are measurable, they are random variables, so by theorem... Oh, okay. I see what I'm doing here. Okay, so since these things are measurable, so they are measurable from R to R, they are random variables. And we know that they are measurable by theorem 1.3.5 because f upper delta and f lower delta are semi-continuous functions, and 1.3.5 tells us that semi-continuous functions are measurable. So now f upper delta of x, which is the limit as delta decreases to 0 of f upper delta, this is also the limit as n goes to infinity of f upper 1 over nx. Because instead of decreasing, if we're decreasing delta to 0, it suffices to decrease delta to 0 in this particular way, by taking the limit as n goes to infinity of 1 over n. And f0, which is the limit as delta decreases to 0 of f delta, which equals the limit as n goes to infinity, f1 over n, are random variables, i.e. they are measurable. So the only reason that I'm using the notation random variables here, I guess this isn't really necessary, but what we proved previously is that limits of random variables are measurable. Did we actually prove that, or did we just prove it about limbs and supremums and infimums? This should be fine though, because this is really what we want. What we want is that f upper f upper 0 and f lower 0, we need these to be measurable from R to R. And the only reason I'm using the referring to them as random variables is that we proved things about limits of random variables being random variables. And so I wanted to invoke those. Okay, so there might be a few details here that I might be missing. I might include those in the end if I feel that they're absolutely necessary. But I think this is if there's anything I'm missing here, it's not a big deal. Okay. So we also know that sums of measurable functions are measurable. So f0 minus f upper 0 minus f lower 0 is measurable. Now, the singleton set containing 0 is closed. And so if we take the inverse image of this, this is all x such that f0x minus f0x is 0. So this is all points x such that f upper 0 of x is equal to f lower 0 of x. And so this is measurable. And measurability is closed under complement. So if we look at the collection of points where f upper 0 is not equal to f lower 0, this is precisely equal to the complement of where f. So this is a set of discontinuities. And so this thing is measurable. But f0 is not equal to f0 is precisely the set of discontinuities. Oh, that was weird. Of f. And so we've proven that the set of discontinuities of f is measurable, and that's what we wanted to prove, and so now we are done. So I said that we're done with this exercise, but then I thought about it a little bit more, or even as I was explaining the exercise, I felt like something was missing at the end here. So there's sort of two things that I don't think I explained really well. First of all, f0 and f upper 0 and f lower 0 are indeed measurable because if you write it out, and I'll show you how to write it out, they can be written in terms of limits and supremums, and which means that they can essentially be written in terms of infimums and supremums, which thus makes them measurable, as we have seen. But the more important thing is, I know that I didn't do a good job of showing that the set of points where f upper 0 is not equal to f lower 0 is precisely the set of points where f is not continuous. And indeed, this is not something that I think... this is something that is one of those things that you look at it and you think, oh, this is straightforward, but it really isn't. So let's go through it. Recall that f is continuous at x if and only if, and there's many ways to define it, but here's one definition. F of x must equal the lim inf as y goes to x of f of y, but it also must equal the lim sup as y goes to x of f of y. And in this case, you say the limit as y goes to x of f of y exists, and it's equal to f of x. Okay. So, we must prove that f upper 0 of x equals f lower 0 of x if and only if f of x equals lim_inf y goes to x fy equals lim sup y goes to x of f of y. Alright, so let's do this. Suppose f upper 0 of x equals f lower 0 of x. Then f lower 0 of x, this is by definition the limit as delta decreases to 0 of f lower delta of x, which is, and then we write it out a little bit more, this limit, this infimum of y in b delta x of f of y. And so now we can see why this is actually measurable, because this limit as delta decreases to 0 of the infimum, this can also be written as the what is this? I believe this can be written as the supremum of all what is it? When you have a lim sup, you can write it either as a limit of a supremum or an infimum of a supremum. And so if you were to take this and write it as a supremum of an infimum, then you would have the fact that this is measurable. Okay, and so now what we have here is this is the entire ball, this infimum here is taken over the entire ball of radius delta centered at x. By the way, there could be some argument as for like, well, I don't know. Yeah, this is fine. Okay, so anyway, so this is the infimum where y is taken over the entire ball of radius delta centered at x. But if we recall, for the lim_inf definition, you actually need a punctured neighborhood. You're taking the limit, so you're not talking about what's happening exactly at that point. And so we need to handle that. And so if you include the point, so if you remove that point from this, if you remove that center, then this infimum could only possibly get bigger. And so this is less than or equal to the limit as delta decreases to 0 of the infimum of y in the punctured neighborhood of radius delta centered at x of f of y. And now this is precisely the lim_inf as y goes to x of f of y. The lim_inf is always less than or equal to the lim sup as y goes to x of fy. And this, recall, is the limit as delta decreases to 0 of the supremum of y in ball radius delta punctured at x of fy. And now we want to include f of x back in here. And so when we're increasing the size of the set over which we're taking the supremum, this set is only possibly getting bigger, and so this is less than or equal to the limit as delta decreases to 0 of the supremum over all delta in the ball of radius delta centered at x of f of y, not punctured this time. And this is precisely the limit as delta decreases to 0 of f upper delta of x, which is f upper 0 of x. So this should rather say sense, because this always holds. But we know that f upper 0 of x equals f lower 0 of x. Equality holds throughout. So in particular, we have lim_inf as y goes to x of f of y equals lim sup as y goes to x of f of y. Alright, so that's part of it. We need the lim inf to equal the lim sup, which we now have. But now we actually need equality. We need both of these things to equal f of x. Also, f of x is less than or equal to the supremum over all y in ball of radius delta centering at x of f of y. So taking delta down to 0 gives us f of x is less than or equal to f upper 0 of x. And if we do the same thing, but with infimums and reversing the inequalities, f0, or f of x, is also going to be greater than or equal to f0 of x. And so, since f upper 0 of x equals f lower 0 of x, fx equals f upper 0 of x. Right, because we've proven before that f upper, right, so f upper 0, no, f lower 0 is less than or equal to f of x, which is less than or equal to f upper 0 of x, but f upper 0 of x equals f lower 0 of x, and so equality holds throughout. And so f equals, in particular, f upper 0 of x, which we know, since by the large inequality that we have before, this is also equal to lim inf, as y goes to 0 of f of y, which is also the lim sup, as y goes to x of f of y. Thus, f is continuous at. Okay, that's not a good thing. And now it's better. Things were bad, but now they're good. Forever. So we've proven that f is continuous at x. So if f upper 0 of x equals f lower 0 of x, then f is continuous at x. Conversely, suppose f of x equals lim inf as y goes to x of f of y equals lim sup y goes to x f of y. So this is saying, so suppose that f is continuous at x. Note that for any real value a, max of a and x and min of a and y are continuous functions. No, min of a and x. These are continuous functions of x. And this is because you can just sort of think about it visually. If you take the max between a and x, if x is less than or equal to a, then you're just going to have a horizontal line at a. But if x is, if your input, if x is greater than a, then the output is just going to be x. And so you're going to have a horizontal line which will eventually just become the line y equals x. And so this is obviously going to be a continuous function. You can prove it rigorously if you want to. I don't want to. Similarly, the min is a continuous function. Okay. So we take the supremum over y in beta delta, or b delta x of f of y. So this is actually the maximum of f of x and the supremum over all y in, it's happening again, supremum over y in b delta punctured x of f of y. Right? Because if you want an upper bound for this set here, and if you remove a point, then yeah, this is just how you would get this. Supremums are like maxes. Supremums for finite sets are just maxes. And this is a maximum over just two elements. Okay, so this supremum equals this maximum. And if we take the limit as delta decreases to 0, what we end up with, okay, come on, computer, we're almost done here. Just hang in with me. Okay, so hang in there. So f upper 0 of x, this is precisely the limit as delta decreases to 0 of the supremum of this thing. So it's precisely the limit as delta goes to 0 of this maximum that I've written here. But because maximum functions are continuous, you can bring that limit inside. So this is actually the maximum of f of x, and the limit as delta decreases to 0 of the supremum of all y in this punctured radius of f of y. And so this is the maximum of f of x and the lim sup as y goes to x of f of y. But we've proven that these two things are, or we're assuming that these two things are the same since since we're assuming that f is continuous at x. So this is precisely f of x. Likewise, f lower 0 of x, so this is the limit as delta decreases to 0 of inf of y in b delta x, and this is of f of y. So this is the minimum of f of x, and here what we do is we know that infimum over all y in b delta x of f of y is the minimum of f of x and the infimum over all y in the punctured ball of radius delta centered at x of f of y. And then we just take limit as delta decreases to 0 on both sides and take that limit as delta decreases to 0 and bring it inside the minimum on the right hand side. And we end up with this. Limit as delta decreases to 0 of the infimum over all y in this punctured ball f of y. And so this is the minimum of f of x and the lim inf as y goes to x of f of y, which is f of x. So f upper 0 of x equals f of x, which also equals f lower 0 of x. So f upper 0 of x equals f lower 0 of x. And hence, f is continuous if and only if f upper 0 of x, f is continuous at x, if and only if f upper 0 of x equals f lower 0 of x. So what we proved previously is that, what did we prove? We proved that f upper 0, we proved that the set on which f upper 0 is not equal to f lower 0, this set is measurable. And now we've proven that the set where f upper 0 is not equal to f lower 0 is precisely the set of discontinuities of f. And hence, the set of points at which f is discontinuous is measurable. And so now we are done with the exercise.